My name is Reagan Wakefield. My name is Reagan Wakefield, and this is my Physics 2211 Motion of a Falling Object lab. The purpose of this lab is to observe the motion of an object that is dropped from rest and falls somewhat slowly straight down. We will do this by constructing an experimental model and two computational models. One computational model will include the effect of gravity, and the other model will include the effect of gravity and drag. The first fundamental physics principle used in this lab is Newton's second law, which states that an object's acceleration depends on the force acting upon the object and the object's mass. We will derive necessary formulas from this principle in the next slide. The second principle is drag. Drag occurs due to air particles, and it is in the opposite direction of the object's motion. In this lab, drag is in the positive y direction. Finally, gravity is a force that pulls objects toward their mass. In this lab, the object is pulled towards Earth. For the experimental model, we will be dropping an eraser from a position of rest and investigating its motion through an online tool called Tracker. The system is the falling object, in this case an eraser, and the surroundings are everything else around the system, such as gravity and drag. For the two computational models, we will be using GlowScript. We will use numerous important formulas in GlowScript. The first formula is Newton's second law, which states that net force is equal to the change in momentum over the change in time. For Newton's second law, we derive two other formulas called the position update formula and the velocity update formula. The position update formula states that final position equals initial position plus average velocity times the change in time. The velocity update formula states that final velocity equals initial velocity plus net force divided by mass times the change in time. In addition, the force due to gravity is equal to the mass of an object times the acceleration due to gravity, and it points in the negative y direction. As we will see later on in the presentation, both computational methods will overpredict the position of the eraser when compared to the experimental model. The computation model without drag, however, will overpredict the position the most. I use this video and tracker to track the motion of the object by plotting its position as a function of time. I chose my axis so that up is positive y and down is negative y, resulting in a downward sloping graph of position versus time that you can see in the right-hand side of the video. Moving on to the computational model, here are some excerpts of my code from the model without drag. The eraser begins at rest, so I set my initial position and velocity to be 0, 0, 0. I also set my delta t to be 0.033. I obtained this by dividing the total time of the video by the number of frames. Finally, since the drag force is not being applied in this model, I set the proportionality constant b equal to 0. The excerpt on the right showcases how I calculated the force due to gravity. I set the net force to equal the weight of the eraser. Here are excerpts of my code from my computational model with drag. Most of the initial conditions remain the same. However, since we are now including drag, I set the proportionality constant b equal to 0.0017. I obtained this number through trial and error until the model predicted a final position that was close to the final position of the experimental model. Another difference is that the new force now contains both the force due to gravity and the drag force. Here's a position versus time graph of the data from the experimental model and both computational models. As you can see, the data is similar at the beginning, but as t increases, the data begins to diverge. Both computational models overpredict the position of the eraser when compared to the experimental model, but the model with gravity overpredicts the position the most. This is most likely due to drag being absent from the gravity model. Drag force points opposite to the motion of the falling object, and the computational model with only gravity does not account for this opposing force. Now I'll answer some follow-up questions. The first question is, do any of the models predict terminal velocity? A terminal velocity is reached when the drag force is equal and opposite to the weight. The computational model with gravity and drag is the only one that predicts a terminal velocity because it factors in drag. This is shown in the graph as it points from the drag computational model begins to flatten out towards the end, signaling terminal velocity. The second question is, what if we threw the eraser rather than letting it drop from rest? The graph on the right shows the velocity if the eraser was thrown, and we can see that the graph shifts because we already have an initial velocity going in the negative y direction. The two graphs show that the terminal velocities would eventually be the same, but the time it would take to reach them would differ because drag force is no longer the same. So it would take longer for the object at rest to reach terminal velocity than the thrown object. Finally, I'll identify some sources of error that I may have had in the lab. The main error was human error with GlowScript and Tracker. This is only my second time using these technologies, so I could potentially have small errors. Specifically, I had issues with finding the right proportionality constant that would cause the final position in the computational model with drag to match the final position of the experimental model. I did trial and error until I got as close as possible. Thank you so much for watching this video. I hope you enjoyed.